in the silence between particles, where matter dissolves into a trembling haze of probability, reality reveals a secret it was never meant to share. What appears to be emptiness is not empty at all. It is a vast and intricate architecture, woven from forces older than stars, older than time, older than the first spark that scattered light into the newborn universe. Beneath everything that exists lies a hidden framework, a shimmering, unseen ocean where the rules of nature quietly converge. Physicists once imagined the void as a perfect nothing. But the deeper their instruments reached, the stranger the darkness became. Space-time rippled like a living surface, its fabric quivering with ghost-like fluctuations. Each rise and fall whispering of an underlying order. Quantum fields pulsed beneath atoms, vibrating with patterns no theory had predicted. Galaxies drifted across a cosmic lattice that should not exist, a lattice too precise, too synchronized, too elegant to belong to chaos. Here, at the boundary between existence and nothingness, the universe carries a contradiction it struggles to hide. The foundations of reality behave as if arranged, as if guided by some invisible blueprint. And yet, according to the laws of physics, such structure has no right to be there at all. Something holds the universe together, a hidden scaffold beneath every star and every breath of empty space. It is organized. It is deliberate. It is impossibly fine-tuned. And if this secret structure truly exists, then everything humanity thought it understood about the nature of reality is only the surface of something far more mysterious. The search for the universe's hidden structure did not begin with a grand revelation or a bold declaration. It emerged quietly, like a faint tremor beneath the noise of ordinary experiments, noticed only by those who had learned to listen to the silence between equations. In the early decades of the 20th century, when physics was undergoing its violent transformation into the quantum age, the first clues appeared small, fragile, and easily dismissed. Yet they persisted, and over time they formed a whispering trail that would lead scientists to one of the strangest ideas ever encountered: the possibility that reality possesses an underlying architecture far more intricate than any law had predicted. It began with Einstein's struggle to understand the very stage on which the universe performed its ancient play. He had shown that gravity was not a force, but the curvature of space-time itself, fluid geometry capable of bending, stretching, and carrying the motion of planets and light. But in private letters and late-night notes, Einstein often confessed unease. The fabric he had revealed behaved like a material, yet he had never truly explained what the fabric was made of. And when he attempted to unify gravity with electromagnetism, when he tried to reveal a single foundation beneath the forces of nature, he found only incomplete threads. His equations resisted him, as if guarding a secret they did not wish to surrender. The deeper he descended, the more the continuum of space-time felt like the surface of something even deeper, something he could sense but not define. Decades later, as quantum electrodynamics matured under the hands of Dirac, Schwinger, and Feynman, the physics of the vacuum began to behave in ways that defied intuition. The vacuum was not empty. It was restless, simmering with virtual particles that flashed into existence and vanished before they could be captured. Richard Feynman, who understood this ocean better than most, once remarked that the vacuum is the most violent place in the universe. Yet even through the chaos, patterns emerged. The fluctuations that danced beneath the surface were not entirely random. They carried a strange regularity, a rhythm that felt more like structure than storm than. In 1948, Hendrik Casimir revealed something astonishing. By placing two uncharged metal plates close together in a vacuum, created a space so small that only certain wavelengths of virtual particles could exist between them. The plates moved, not from electricity, not from magnetism, but from the pressure of the vacuum itself, pressure, created by the difference in allowed fluctuations inside and outside the plates. This force, now called the Casimir effect, confirmed that empty space contained energy, but more subtly, it suggested organization. Only specific wavelengths fit. Only specific modes were allowed. It was as if the vacuum behaved like a physical medium with rules that hinted at an underlying geometry. Casimir had not been searching for hidden structure. He was exploring quantum electrodynamics. Yet his discovery opened a quiet doorway that few recognized at first. If the vacuum displayed constraints, patterns, and selective behaviors, then, beneath the randomness of quantum noise, there might be something else. Something architect you are. As the decades passed, more hints surfaced, each small on its own, yet impossible to ignore when placed side by side. In the 1960s, radio astronomers Arno Penzias and Robert Wilson detected a faint hiss of persistent microwave glow coming from every direction in the sky. What they had stumbled upon was the cosmic microwave background, the afterglow of the Big Bang, a radiation field older than the oldest star. This ancient light became a cosmic map, and when satellites like COBE, WMAP, and eventually Planck charted it with exquisite precision, subtle patterns appeared. The fluctuations in temperature supposed to be random carried harmonics, alignments, and relationships that seemed to organize to arise by chance. Some called it the axis of evil, cryptic large-scale alignment that defied expectations and hinted at something underlying the entire structure of the cosmos. Scientists debated fiercely. Some argued the patterns were statistical illusions, artifacts of measurement. But others, especially cosmologists studying inflation, noticed that the harmonics matched predictions of a deeper field, one that shaped space-time before atoms existed. Alan Guth's inflation theory, born in the early 1980s, suggested that a quantum field had driven the explosive expansion of the universe in the first instant after the Big Bang. But for this field to behave the way it must have behaved, it required astonishing uniformity. The inflationary field could not be chaotic or random. It needed coherence, a property more akin to a structured foundation than a turbulent sea. Here, the whisper grew louder. The early universe had unfolded with surprising order. The vacuum, which should have been volatile and directionless, displayed constraints. And the cosmic microwave background held echoes of a geometry predating all matter. Meanwhile, in an entirely different field, particle physicists working at CERN and other accelerators noticed peculiar resonances in the quantum vacuum. When high-energy collisions cleared matter away for fractions of a second, what should have been empty behaved with stubborn consistency. Fluctuations rose to specific energy levels. Certain patterns repeated more often than chance should allow. The vacuum responded as if it held an internal structure, a hidden grid that dictated what could and could not appear. None of these phenomena were initially connected. Einstein had sought unity. Casimir was exploring quantum electrodynamics. Microwave maps were tools for cosmology. Particle accelerators probed the smallest building blocks of matter. Each field was isolated, each discovery confined to its own domain. Yet, the underlying theme was unmistakable. Wherever scientists looked deep enough beyond atoms, beyond forces, beyond galaxies, they found not chaos, but coherence. Even Stephen Hawking, who spent decades studying the boundaries of black holes, detected mathematical hints of underlying order. Hawking radiation, predicted through the marriage of relativity and quantum field theory, required the vacuum near a black hole's horizon to behave with startling consistency. Virtual particles did not simply appear and vanish randomly. They did so in patterns, responding to curvature in ways that suggested an intimate relationship between spacetime and quantum fields. This relationship hinted at a deeper substrata unifying backdrop upon which both gravity and quantum mechanics were performing. The Planck Observatory, launched in 2009, delivered the most detailed map of the cosmic microwave background ever created. Its data shook cosmology. Temperature fluctuations revealed a remarkable symmetry at large scales. The distribution of hot and cold spots followed statistical rules, too precise, too clean, to be attributed to chance. Subtle correlations stretched across vast distances, linking regions of space that, according to relativity, should never have communicated. The standard models struggled to explain these alignments, without invoking something beneath spacetime itself, some underlying architecture. that existed before inflation. Stretch the cosmos through these discoveries. A strange picture began to form. It was not yet clear, not yet proven, not yet fully realized. But the hints converged. The vacuum followed patterns. Space-time displayed harmonics, and quantum fields responded to invisible constraints. The universe behaved as though controlled by a hidden scaffold. Physicists at CERN detected vacuum decay thresholds more delicate than expected, suggesting a fine-tuning of the Higgs field. This fine-tuning was so improbable that some described it as unnatural, not because it was magical, but because it was too precise to arise from randomness. Every parameter that allowed matter to exist, mass, charge, coupling strength, sat on a razor's edge. A slight deviation would erase atoms, stars, chemistry, and life. Yet these parameters remained stable, held in perfect balance, as though fixed into place by a deeper foundation. Even unrelated experiments echoed the same quiet theme. Atom interferometry revealed coherence in vacuum behavior at astonishing precision. Superconducting circuits used to probe quantum fluctuations detected repeating signatures in what should have been statistical noise. And at the edges of astrophysics, dark energy surveys uncovered a universe accelerating with a smoothness that felt deliberate rather than chaotic. The expansion was uniform, steady, almost eerily controlled, as though responding to a field with embedded symmetry. No one had been searching for hidden structure. They were searching for forces, particles, origins, patterns in ancient light. Yet the universe insisted on showing them something more. In every domain where randomness should dominate, order appeared. And as the data accumulated, the possibility that this order was merely coincidence began to fade. A growing number of theorists started to wonder aloud. If space-time behaved like a medium, if quantum fields rippled through patterns too stable to be accidental, if the vacuum itself favored certain configurations, then perhaps reality was not built on chaos at all. Perhaps it rested upon a deeper architecture, mathematical, geometric, and woven into the very essence of existence. The more evidence surfaced, the more unsettling the implications became. The structure was subtle, almost hidden, detectable only through precision instruments and mathematical reconstruction. Yet its presence was undeniable. It was the same in the smallest vacuum fluctuations and the largest cosmic maps. It appeared in unrelated experiments across continents and decades. A quiet, coherent signature beneath the noise. By the time the 21st century reached its second decade, scientists across particle physics, quantum theory, and cosmology found themselves staring at a shared mystery. They had not chosen the puzzle had chosen them. Casimir's plates, Planck's sky maps, Einstein's equations, Hawking's horizons all pointed toward the same whispering truth. Reality might possess a substructure, far more organized than randomness should permit. What emerged from these discoveries was, it's not yet a theory, not yet a model, but an emotion. A feeling shared by researchers who, though separated by fields and generations, recognize the same haunting pattern. Beneath space-time, beneath matter, beneath all known forces, something waited, something structured, something deliberate, something that should not exist according to the laws of physics. And yet, undeniably it was there. The first hints of hidden structure were unsettling, but they did not yet command fear. Scientists assumed the irregularities in the vacuum, the faint harmonics in ancient light, and the quiet coherence in quantum fields were simply curiosities strange. Yes, but surely explainable with better instruments or improved mathematics. Yet as the evidence accumulated and the measurements sharpened, a startling realization swept across the scientific world. The universe was behaving in a way it should not behave. The shock did not come from one discovery, but from an uneasy convergence. The vacuum, once thought to be an empty stage on which matter performed, revealed itself to be active, energetic, and impossibly structured. Quantum fields, which should have flickered in chaotic disarray, instead displayed patterns of stability so improbable that even statisticians hesitated to assign probabilities. And on the largest scales, where galaxies floated in cosmic isolation, The geometry of space-time showed a smoothness that defied randomness. Everything, from the inconceivably tiny to the unfathomably vast, seemed to follow a hidden order. This order was not part of classical physics. It violated the expectations of a universe born from chance. It contradicted the wild, unstructured beginning expected from a Big Bang governed solely by thermodynamics. It pushed against the idea that reality emerged spontaneously from nothing. The more scientists explored, the more the universe resembled something tuned, balanced on parameters so precise that even the slightest deviation would erase stars, atoms, or the possibility of life. The shock began in laboratories, where emptiness was studied with mathematical attention. The vacuum was meant to be featureless. It was supposed to be the absence of everything, a void where nothing existed. Yet vacuum energy predicted by quantum electrodynamics and reluctantly accepted by physicists refused to behave like nothingness. It surged with zero-point motion, produced pressure of measurable force, and responded to boundaries with an elegance no one expected. The Casimir effect had been the first sign. But as more experiments explored ultra-cold environments and precise quantum states, the vacuum displayed an even stranger property. It remained stable in classical understanding. A vacuum with energy should collapse or explode. It should fluctuate wildly. But the vacuum of the real universe did neither. Instead, it held its value with astonishing precision. It's precise that if its energy differed by even 1 part in 10,120, the universe would have torn itself apart in the first fraction of a second. This unimaginable fine-tuning became one of the great puzzles of modern physics. No equation of classical mechanics, no law of thermodynamics, no principle of probability could justify such balance. It appeared as though the universe had been quietly adjusted, held in place by a hidden mechanism. The quantum fields that filled every point of space were expected to behave like chaotic seas. But they did not. They exhibited coherence. They arranged themselves into stable configurations. Virtual particles appeared in patterns that repeated across experiments, across time, across theoretical simulations. And when the fields interacted with gravity, they did so with an uncanny consistency that suggested the underlying space-time itself was responding to rules. Beyond general relativity, space-time. Einstein's great stage revealed its own secrets when the cosmic microwave background was mapped with increasing precision. The temperature variations only millionths of a degree from one region to another followed harmonics reminiscent of a musical instrument. They were smooth where they should have been jagged, aligned where they should have been random. Entire regions of the sky, separated by distances that no physical signal could have crossed, showed matching features. The shock grew deeper. The universe behaved as though it had been synchronized before space-time even existed. When the Planck mission released its final data set, cosmologists stared at maps that resembled blueprints. They saw order imprinted into the earliest moments of the universe, order that could not have arisen from a spontaneous explosion. Something had guided the formation. Something had smoothed the chaos, shaped the fluctuations, and carved pathways that gravity later followed to build galaxies. Physicists gathered in conferences and private discussions, attempting to reconcile the impossibility with the equations. How could a random universe produce a vacuum so stable, fields so coherent, and geometry so smooth? They debated whether an unknown force could be responsible, whether inflation alone could solve the mystery, whether quantum gravity might someday reveal an explanation. Yet every attempt only deepened the contradiction. If randomness governed creation, then structure should have been fragile, fleeting, and accidental. But the structure they observed was robust, persistent, and pervasive. This tension reached its peak with the fine-tuning problem. The constants of nature, the mass of the electron, the strength of the electromagnetic force, the ratio of proton mass to neutron mass. The cosmological constant all sat at values that seemed deliberately chosen. A small change in any one of them would extinguish the possibility of complex chemistry. A larger change would extinguish the universe itself. Yet nothing in the known laws of physics compelled these constants to hold their specific values. They simply did. They remained fixed, unwavering, as though pinned down by a deeper layer of reality. The shock, for many scientists, came not from the idea of fine-tuning itself, but from the magnitude of it. The odds of a universe with the right conditions for stars, planets, and living complexity were astronomically low. But the odds of a universe with stable vacuum energy, synchronized cosmic harmonics, and perfectly balanced quantum fields were so low that no probability scale could meaningfully express them. Some compared it to balancing a pencil on its point for billions of years. Others compared it to winning every lottery ever held, every second. Since time began, the universe was not behaving as an accident. It was behaving as something shaped. The scientific community did not rush to metaphysical interpretations. They resisted the idea of external influence, preferring to search for natural mechanisms. But even natural explanations posed challenges. If inflation had smoothed the early universe, why had it done so with such precision? If quantum fields obeyed harmonics, why did those harmonics match the structure of cosmic geometry? If the vacuum held energy, why did its value align with the needs of galaxies to form billions of years later? Each explanation seemed to require another hidden layer, another field, another symmetry, another principle that had not yet been discovered. The missing piece felt less like a particle, more like a blueprint. The contradiction between classical expectations and observed reality became a source of quiet discomfort in scientific circles. Classical physics assumed that the universe had no reason to be orderly, that it should have emerged from randomness and followed the path set by blind forces. But the universe observed through telescopes' detectors, and equations did not resemble the universe expected in classical thought. It resembled something else, a cosmos built upon an invisible foundation. The shock deepened when studies of dark energy revealed another layer of impossible stability. The expansion of the universe was accelerating with a smoothness that seemed unnatural. If dark energy were truly random or chaotic, regions of the universe would expand differently. Large-scale structure would tear, warp, or collapse. Yet dark energy behaved with perfect uniformity. Even across distances of billions of light years, its behavior remained consistent. This consistency implied a field one that permeated all of space and time, obeying constraints that no classical theory could enforce. As scientists confronted these discoveries, many found themselves wrestling with a question that felt almost forbidden in academic discourse. Why does the universe follow rules so clean, so precise, so improbably tuned that they appear constructed? No one dared phrase it that way in published papers. But in seminars, in private conversations, in late-night discussions with colleagues, the idea emerged again and again. The universe looked engineered not by intention, but by structure. It behaved as though something beneath it, something deeper than quantum fields, had shaped the raw chaos into patterns. This interpretation did not require a designer, nor did it require intelligence. It required something even stranger, a level of physical order so fundamental that all known laws emerged. From it like ripples from an unseen source, some theorists proposed that this hidden source was a quantum field, far more fundamental than any yet discovered. Others proposed that space-time itself was emergent, rising from microscopic units of geometry. Still others argued that the universe was one of countless universes in a vast multiverse, where only those with stable parameters survived. But even these explanations carried philosophical weight. If the universe was selected, if it emerged from survival, if its laws were shaped by deeper rules, then it was not accidental. It was the product of structure. The shockwave spread to fields beyond physics. Philosophers spoke of existential tension. Astrobiologists questioned whether life was an inevitable outcome once structure existed. Even mathematicians found themselves uneasy with the elegance of physical laws. If reality was built on structure, then perhaps mathematics was not merely a tool to describe the universe. Perhaps it was the universe. Yet the greatest shock remained in the data. The vacuum was not empty. Quantum fields were not chaotic. Space-time was not loose fabric. The universe was not careless in its construction. It was consistent, predictable, harmonized. Physicists stood at a crossroads. If the universe looked constructed but no constructing intelligence was required, then what was the architect? A fundamental symmetry? A deeper theory? A hidden layer of reality? No one knew. But the contradiction was unavoidable. A random universe should not behave this way. A chaotic beginning should not lead to such precise structure. A vacuum filled with violent fluctuations should not remain so perfectly balanced. And yet, the universe held its form. It kept its constants. It behaved like a finely tuned machine built on rules older than time. The shock lay not in the mystery itself, but in its persistence. Whatever was beneath reality, whatever secret structure held the cosmos together. It was not an illusion. It was not noise. It was not chance. It was real. And for the first time in scientific history, humanity began to see its outline as the 20th century slipped into the 21st. The search for the universe's hidden architecture entered a new and extraordinary phase. The quiet hints that once flickered at the edge of scientific perception were now being pursued by instruments of unprecedented sensitivity. The mystery that had once been whispered between experiment and theory began to speak more clearly. And what it revealed was stranger and more structured than anyone had expected. The deeper scientists looked, the more the universe behaved like a layered manuscript, each page revealing a pattern more deliberate than the last. The simple notion of space as an empty container began to dissolve. What replaced it was an image far more intricate, a cosmic fabric woven with invisible threads, vibrating with ancient harmonics. Carrying secrets buried in the earliest light, the Planck satellite became one of the first great instruments to expose this subtle architecture. Launched by the European Space Agency, Planck was designed to map the oldest radiation in the cosmos, the faint afterglow of the Big Bang. This light, older than any star, carried the imprint of the universe's birth. And when Planck scanned the sky with exquisite precision, its detectors captured a map that stunned cosmologists. The cosmic microwave background, which had been expected to hold mostly random fluctuations, instead displayed delicate patterns. Temperature variations arranged themselves in structures that followed mathematical relationships. Even the noise, the faint static of the early universe carried correlations extending across vast stretches of the sky. These were not chaotic scars from a violent beginning. They were harmonics, almost musical in nature, as if space itself had once rung like a vast cosmic instrument. The frequency modes matched predictions of primordial quantum fields, but with a precision difficult to reconcile with randomness. It was as if the early universe had been shaped by an organizing principle, smoothing and tuning the first fluctuations of energy and matter before any galaxy could form. Planck's maps went beyond confirming inflation. They hinted at something beneath inflation, a deeper script that shaped the very stage on which inflation unfolded. Mathematical reconstructions of the primordial plasma revealed faint grid-like patterns in the distribution of fluctuations, too subtle for earlier satellites to detect. These patterns, though not literal grids in space, resembled the structure of a field that had been constrained by underlying geometry. It was a geometry that existed at scales far smaller than space-time itself, almost as if space-time arose from something beneath it, something quantized, structured and ancient, while Planck looked back to the birth of the universe. Another instrument listened for ripples passing through the present. LIGO, the Laser Interferometer Gravitational Wave Observatory, was built to detect vibrations in space-time caused by cataclysmic events colliding black holes, merging neutron stars, and the violent dance of massive objects. When LIGO first detected gravitational waves in 2015, it opened a new window into the cosmos. But hidden within those waves, buried in the interference patterns, researchers began to notice anomalous deviations that did not match the predictions of pure general relativity. These deviations were faint, hovering at the edge of statistical confidence, but they appeared in multiple signals, always in similar form. The waves seemed to carry hints of a granular structure in space-time, tiny discontinuities, or correlations, that could not be explained by noise alone. Some theorists propose that LIGO might be brushing against the Planck scale, where space-time is expected to reveal its deepest nature. If space-time were composed of fundamental units, the passing waves might interact with this underlying texture in subtle ways. In classical relativity, space-time is smooth, continuous, and unbroken. But if quantum gravity is correct, if space-time emerges from a deeper substrate, then LIGO's anomalies might represent the first glimpses of that hidden foundation. The waves moved as though traveling across something almost crystalline, a medium with microscopic structure. The idea remained controversial, but it fueled a growing fascination. Perhaps the universe's stability and order arose, because space-time itself was not continuous at all, but woven from discrete, interconnected elements. Quantum simulations added another layer of intrigue. Using superconducting qubits and advanced quantum processors, researchers simulated vacuum fields and particle interactions with increasing fidelity. These quantum systems, isolated from environmental interference, behaved in ways that mirrored the dynamics of fundamental fields. The simulations revealed a surprising coherence, a tendency for certain patterns of vacuum fluctuations to repeat, to self-organize, as if following a hidden set of instructions. The vacuum, expected to be turbulent and unpredictable, instead displayed emergent order. In simulation after simulation, quantum fields settled into configurations with recognizable structure. The fluctuations formed webs of stability, suggestive of an interacting network rather than independent randomness. These emergent structures did not arise from imposed symmetry. They arose spontaneously, hinting that real vacuum fields might also harbor organizational tendencies. Particle detectors provided real-world counterparts to this simulated behavior. At facilities like CERN and Fermilab, researchers probed high-energy collisions that momentarily cleared matter away and revealed the vacuum's restless dance. Within the noise patterns appeared fine structures in the distribution of particle momenta, correlations between seemingly independent events, and energy thresholds that repeated across experiments. These were not artifacts of technology. They persisted across detectors, across years, across upgrades. The vacuum seemed to resist being a simple sea of randomness. It behaved like a medium with rules. The shock intensified when researchers analyzing zero-point energy observed symmetries that defied explanation. Zero-point energy, the irreducible minimum energy of a quantum system, had been understood as a chaotic mix of modes. Yet measurements revealed relationships between these modes, as if the energy distribution were following a blueprint. Some symmetries resembled patterns predicted by string theory. Others hinted at deeper geometric constraints predicted by loop quantum gravity. But no single theory could explain all the observed features. The structure appeared to transcend existing frameworks, existing not within a particular theory, but beneath them all as the data accumulated. The idea of vacuum texture began to take hold in theoretical discussions. This texture was not physical in the conventional sense. It did not resemble a material or a lattice. Instead, it described an underlying pattern in the behavior of fields, an imprint of something hidden within the equations themselves. The texture revealed itself through correlations in quantum noise. What should have been statistical scatter, with no preferred direction or scale, instead produced repeating signatures. At first, these repeating features were dismissed as observational artifacts. But with each new experiment, the patterns reappeared, more refined and more precise. Noise ceased to be noise. It was a signal in disguise. Some researchers likened it to discovering the grain in a piece of wood. The grain was not obvious at first glance, but under the right light, the natural pattern emerged. The vacuum displayed a similar hidden grain, a directional preference, a subtle anisotropy, a structure that should not exist in a truly random universe. Mathematical reconstructions of vacuum fluctuations, using advanced statistical techniques, revealed networks of correlation extending across scales. These networks resembled fractal-like webs, not in their visual form but in their mathematical behavior. At every level of magnification, the same relationships reappeared. This self-similarity suggested that the vacuum might be governed by scale invariant rules, a hallmark of systems shaped by deep underlying principles. theoretical physicists began to grapple with the implications. If vacuum fluctuations followed repeating patterns, then the base layer of reality might not be random at all. Instead, it might be governed by a combinatorial or geometric structure, akin to a quantum code. Some speculated that the universe operated on principles similar to those in topological quantum computing, where stability arises from the underlying geometry of information, not from material forces. In this view, the universe behaved like a self-correcting system, maintaining coherence through rules embedded in its foundation. The cosmic scale offered its own evidence. Dark energy surveys revealed a startling uniformity in the expansion of the universe. Across billions of light years, the acceleration remained smooth, consistent, and mathematically elegant. If dark energy were a random field, its effects would vary across regions. But instead, the expansion behaved as if responding to a global pattern, one that's extended across the entire cosmos. Combined with the Planck data, this suggested that the universe might be shaped by a foundational symmetry, a symmetry that stretched from the smallest quantum fluctuations to the largest cosmic structures. And if such symmetry existed, it implied a deeper substrate and architectural layer beneath spacetime itself. Some researchers propose that the universe might follow a kind of holographic encoding, where information stored on a boundary governed the behavior of the interior. This idea, rooted in string theory and black hole thermodynamics, gained new relevance as patterns in vacuum fluctuations began to resemble theoretical predictions of holographic systems. Others turned to loop quantum gravity, noting that the grid-like features emerging, cosmological reconstructions, resembled the spin networks predicted at the Planck scale. In these theories, space-time emerges from the interactions of fundamental units nodes, connected by links with geometry arising from their relationships. The surprising aspect, however, was not that such models existed, but that nature itself seemed to echo them. The deeper the investigations went, the more the universe behaved like an encoded system, one where stability, coherence, and symmetry arose from the structure beneath reality. These structures did not resemble classical designs or mechanical frameworks. They were more like the architecture of mathematics, the patterns of information, the harmonics of resonance. They hinted at a universe built from relationships rather than material and laboratories. Detectors refined to unprecedented precision captured faint echoes of this underlying structure. In space, telescopes mapped harmonics and alignments that refused to be dismissed. In quantum computers, simulations revealed emergent coherence. And in the mathematics that tied all these observations together, researchers found themselves confronting a profound realization. The universe was not chaotic at the bottom. It was organized. Each discovery peeled back another layer, and each layer revealed deeper complexity. An elegant web beneath reality that no theory had fully predicted. The anomalies no longer looked like errors. They looked like messages. Something beneath existence was beginning to make itself visible, not through a single revelation, but through a constellation of evidence scattered across physics and cosmology. It was an architecture that spoke in fluctuations, waves, harmonics, and correlations. It shaped the vacuum, structured spacetime, and guided the emergence of all physical law. And as scientists stood on the edge of this revelation, one question echoed through every lab, every observatory, every theoretical paper. If the universe behaves as though it is built upon an unseen foundation, then what lies beneath that foundation? As the evidence accumulated, the mystery did not simply grow, it sharpened. What had once been subtle hints and quiet anomalies began to reveal themselves with a clarity that made denial impossible. Every new observation, every fresh stream of data, every refinement of theory pushed the universe further from the domain of chance and deeper into something far stranger, a cosmos arranged by invisible principles, shaped by laws not yet written, held together by a framework that should not exist. The deeper scientists peered, the more the universe resisted the simplicity that classical physics had promised, and soon the mystery did what all great mysteries eventually do. It escalated. It stretched beyond laboratories and telescopes, and entered the realm where the foundations of reality itself trembled. One of the first shocks came from the large-scale structure of the universe, a cosmic architecture that spanned billions of light years. Galaxies, though scattered across incomprehensible distances, formed an intricate web, long filaments, massive clusters, sprawling voids. Seen from afar, it resembled a neural network, a cosmic brain suspended in darkness. But beneath this haunting beauty lurked something even more unsettling. When simulations attempted to reproduce the distribution of matter, they succeeded only if they assumed that some invisible framework guided the gravitational growth. Without it, galaxies would not align the way they do. They would not cluster with such symmetry. They would not form filaments that stretched like strands woven into a cosmic tapestry. Researchers began referring to this dilemma as the cosmic lattice problem, a term that, on the surface, sounded harmless but carried profound implications. If the universe behaved as though resting on a lattice, then the lattice must exist somewhere within the laws of physics. Yet no known equation predicted it. No known force carved it. No known particle traced its skeleton. And still the pattern was there, etched across hundreds of billions of light years, as though the universe had grown along invisible lines. This hidden lattice, reconstructed from surveys like the Sloan Digital Sky Survey and ESA's Euclid mission, was too precise to be a coincidence. Too consistent, too elegant, it mirrored the harmonic scene in primordial radiation, echoing across a cosmic timescale no theory had bridged. Scientists found themselves confronting an uncomfortable possibility. The universe's large-scale structure might not be an emergent accident, but the projected shadow of a deeper geometry beneath space-time. But the challenge did not end there. As the tools of quantum physics improved, another bewildering phenomenon emerged, one that struck at the heart of causality itself. Quantum fields, expected to fluctuate independently across vast distances, showed signs of coherence that defied relativistic limits. Fields separated by distances where no signal could travel appeared to shift in correlated ways, as though synchronized by a mechanism outside of spacetime. These correlations were subtle, buried in noise, but they repeated with statistical force. They were not artifacts, nor were they illusions. The fields behaved as though connected by a hidden layer of reality that ignored the speed of light. This was not quantum entanglement, which operated through well-understood mathematical relationships. This was something deeper, a synchronization of the vacuum itself, an orchestration of fluctuations across distances where causality forbade communication. In classical physics, nothing could behave this way. Yet the quantum vacuum acted as if following instructions encoded across the cosmos. It behaved as though the universe possessed a global blueprint. It's a single underlying structure whose influence extended everywhere at once. Physicists debated this with increasing urgency. Was this synchronization an illusion of measurement? A side effect of mathematical reconstruction? Or was it something real, the first tangible evidence that space-time was not the ultimate stage of reality, but a layer resting upon something more fundamental? At the same time, another anomaly grew harder to ignore: dark energy. The force driving cosmic acceleration behaved with uncanny uniformity. It did not fluctuate. It did not drift. It did not exhibit randomness or local variation. Instead, it expanded the universe as though following a program written into the vacuum. If dark energy were merely a property of space, its behavior would vary as space stretched or curved. But dark energy acted with astonishing precision, adjusting itself to preserve the universe's acceleration with mathematical fidelity. Too many researchers? This smoothness felt more like the stability of a controlled system than the chaos of a natural one. It was as if the universe were maintaining a delicate balance, ensuring expansion continued without collapse or runaway acceleration. Dark energy did not simply exist, behaved, and its behavior implied something, governing it from a level of reality deeper than space-time. The mystery deepened further when Planck scale models revealed unexpected geometric structure at the smallest conceivable scales. The Planck length, 1.6 times 10 to 35 meters, was considered the limit of meaningful distance. Where spacetime's smooth surface was expected to dissolve into quantum foam, but simulations and theoretical reconstructions began to show something that should never have existed at such scales: order instead of chaotic foam. Mathematical models repeatedly produced structured geometries nodes connected by links, forming networks reminiscent of spin networks in loop quantum gravity or the mathematical lattice proposed in causal set theory. These geometries were not created by the models themselves. They emerged spontaneously from the equations. Each simulation, each attempt to probe the Planck scale, produced hints of the same pattern, as if something beneath spacetime insisted on revealing its blueprint. The implications were staggering. If spacetime had structure at the Planck scale, that structure must predate spacetime itself. It must guide its formation, its curvature, its evolution. The universe could no longer be seen as the product of random fluctuations or blind expansion. It behaved as though built upon foundations that had existed prior to time. With each revelation, another pillar of physics trembled. General relativity assumed spacetime was a smooth, continuous entity. Quantum field theory assumed fields fluctuated independently. Cosmology assumed the universe's expansion was driven by a simple property of space. But every new discovery contradicted these assumptions. Every new measurement carved deeper into the mystery. Every new observation added another layer of precision and another layer of impossibility. The contradictions multiplied. If quantum fields synchronized across the universe, spacetime could not be the fundamental limit of interaction. If dark energy behaved as if programmed, the vacuum was not an empty stage, but a dynamic system guided by deeper rules. If the cosmic lattice problem persisted in every map, then the universe's structure emerged from something pre-existing. And if the Planck scale geometry hinted at order, then randomness was no longer the foundation of reality. Physicists found themselves confronting a terrifying possibility, one that had once belonged solely to speculative philosophy. If the hidden structure beneath reality existed, and if that structure governed everything from the behavior of particles to the expansion of galaxies, then the stability of the universe depended entirely on that structure. If it were ever altered, disrupted, or shifted, reality itself could collapse. This collapse would not resemble destruction in the classical sense. It would be a dissolution of the laws of physics, a breakdown of the framework that allowed matter, fields, and spacetime to exist. Without the hidden structure, quantum fields would lose coherence, particles would lose identity, and the geometry of spacetime would unravel. The universe would return to primordial nothingness, a state beyond imagination. Few scientists spoke of this openly. It sounded too dramatic, too catastrophic, too philosophical for careful scientific discourse. But in confidential conversations, the fear was there. If reality was built upon a hidden architecture, then that architecture was the most important aspect of existence and the most vulnerable. Yet the universe showed no signs of instability. The structure, whatever it was, appeared ancient, robust, and deeply entrenched. It had survived cosmic inflation, gravitational collapse, the birth and death of stars. It had held firm through 13.8 billion years of cosmic evolution. The terror lay not in the idea of collapse, but in the profound ignorance surrounding the foundation of reality. Humanity had discovered the walls of the universe's operating system, but not the operating system itself. The mystery pushed scientists into unfamiliar territory. Theoretical physicists admitted that their models, once considered powerful and predictive, now struggled to explain the data. Cosmologists acknowledged that dark energy defied every attempt at classification. Quantum researchers confessed that the vacuum's behavior made no sense within established frameworks. Even string theorists, accustomed to higher dimensional speculations, confronted uncertainties that no version of the theory could fully reconcile. The universe had outgrown the equations designed to describe it, across disciplines, across continents, across decades. The conclusion was becoming impossible to avoid. The universe was not the machine they had expected. It was deeper, more structured, more coherent. And it behaved as though shaped by laws that had not yet been discovered. The escalation of the mystery marked a turning point in the history of science. The deeper the investigation went, the more the universe seemed to whisper the same message. Reality was built on something older than space, older than time, older than the forces that governed matter. That something, whatever it was, lay hidden beneath existence, and for the first time, humanity stood close enough to sense its shape as the hidden structure beneath. Reality grew clearer in observations and simulations. Scientists found themselves standing at the threshold of explanation, and yet the path forward was not singular. It branched into many possibilities, each theory offering a different window into the architecture of existence. None were fully proven. None could claim certainty. But each carried a fragment of insight, a piece of the mosaic that might one day reveal the true foundation of the universe. The search for explanation became a journey through the deepest ideas ever. Conceived by the human mind, a journey across the frontiers of physics where mathematics and philosophy intertwined. And as these theories emerged, they carried with them an unsettling theme. The hidden structure beneath reality might be stranger than anything the classical world had imagined. The first lens through which this mystery could be viewed came from quantum field theory. In this framework, all of existence matter, forces, even empty spaces, nothing more than the behavior of quantum fields permeating the universe. These fields do not rest. Even at absolute zero, where all thermal motion ceases, the fields tremble with zero-point energy, a fundamental vibration that cannot be extinguished. For decades, this zero-point energy had been treated as a mathematical curiosity, a consequence of uncertainty. But now, it appeared to be something more. If the vacuum had texture, if its fluctuations held repeating patterns, if zero-point energy obeyed hidden symmetries, then perhaps this trembling ocean of fields was the true base layer architecture of reality. Perhaps space-time itself emerged from this substrate, rising like foam from deeper quantum tides. In this view, the universe was not built from particles, but from excitations in fields. Matter was not fundamental, it was choreography, stability, coherence, and even geometry were products of the vacuum's internal rules. Yet quantum field theory carried its own weaknesses. Its equations predicted a vacuum energy far stronger than anything observed, strong enough to rip space-time apart. Only through fine-tuned cancellations did the universe remain stable. Why those cancellations occurred, or what caused them, remained unanswered. Quantum fields hinted at structure. They could not explain the structure's origin. Another perspective came from loop quantum gravity, a bold framework that attempted to quantize space-time itself. Instead of treating space and time as smooth continua, loop quantum gravity proposed that the fabric of reality was woven from tiny loops, microscopic structures that formed networks. These networks, called spin networks, create a geometry in the same way woven threads create cloth. At the Planck scale, space-time was granular, discrete, and fundamentally composed of relational units. Some of the hints uncovered by LIGO and Planck appeared to echo this idea. The grainy patterns in gravitational wave interference, the grid-like signatures in cosmic microwave background reconstructions, and the emergent coherence of vacuum fluctuations all bore a resemblance. It's mathematical rather than visual to the spin network idea. If loop quantum gravity were correct, then the hidden structure beneath spacetime was literal. The universe would be a cosmic tapestry woven from loops of quantized geometry, each loop a node in an ancient graph that had existed before the first atom formed. But this view also carried limitations. It struggled to unify with the forces described by quantum field theory, and it had difficulty reproducing some predictions of general relativity. Loop quantum gravity offered a compelling picture, but not yet a complete one. On another front, string theory proposed something even more radical. Instead of particles, strings vibrating in multiple dimensions formed the true building blocks of the universe. These vibrating strings, a tiny filament of energy generated. The variety of particles through their modes of vibration. Like notes played on a cosmic instrument, different frequencies created different types of matter. And beneath all of this, the strings existed within a deeper mathematical harmonia. Hidden symmetry built into the fabric of higher dimensions, string theory predicted entities like brains, extended objects that could stretch across dimensions and serve as scaffolds for whole universes. In some formulations, space-time emerged from the interactions of these strings and brains. Their vibrations created geometry. Their relationships generated force. Their symmetry defined stability. The repeating correlations found in quantum noise, the fine structure in cosmic perturbations, and the mathematical elegance of the Planck scale geometry all echoed predictions from string theory. They hinted at a deeper symmetry, a hidden order that might be the shadow of vibrating strings in higher dimensions. But string theory, too, carried uncertainty. Its equations allowed many possible universes, each with different laws. Without experimental access to its ultra-small scales, string theory remained a powerful, beautiful, but unverified map of reality. A different framework emerged from the study of black holes and quantum information, the holographic principle. This idea proposed that the universe might not be three-dimensional at its core. Instead, all the information describing the universe could be encoded on a distant boundary, a cosmic horizon, much like a hologram encodes. A three-dimensional image on a two-dimensional surface. In this view, volume and depth were illusions arising from encoded information. Space-time, matter, energy, all were projections. If true, then the hidden structure beneath reality was not woven into space but printed on a boundary beyond sight. The coherence of quantum fields across vast distances, the synchronized behavior of the vacuum, and the global smoothness of cosmic acceleration could be explained by a single, unified layer of information. Everything inside the universe would be governed by rules on this boundary. Rules that could maintain stability with astonishing precision. The holographic principle had strong theoretical grounding, supported by work from Gerard T. Hooft, Leonard Susskind, and insights from Stephen Hawking's study of black hole entropy. Yet it, too, carried open questions. What was the boundary? Where was it? And how did information on that distant surface create the intricate world of galaxies, atoms, and consciousness? Another idea, more philosophical yet deeply mathematical, involved vacuum fine-tuning. The constants of nature were balanced with impossible precision. The mass of the electron, the strength of the electromagnetic force, the cosmological constant all seemed chosen. Even small deviations would annihilate stability. Why the universe held these exact values remained a profound mystery, fine-tuning suggested. Design, though, not necessarily in the intentional or intelligent sense. Instead, it suggested a requirement. The universe existed in its current form because only universes with such balance survived long enough to form complex structures. Physical constants might not have been chosen. They might have been filtered. Only those that produced stable geometry endured. This led naturally to another possibility, multiverse selection. In this view, the universe we inhabit was one among countless universes, each with different laws, different constants, different fates. Most collapsed immediately. Others tore apart in uncontrolled inflation. Only a tiny fraction achieved stability. And among those, some produced stars. A smaller number produced heavy elements. A vanishingly small number produced observers. If this were true, the hidden structure beneath reality was not designed for us, was simply the survivor of an ancient cosmic lottery. The lattice-like distribution of matter, the synchronization of quantum fields, and the uncanny precision of dark energy might be consequences of universes that failed. Ours survived because it had structure. In this perspective, structure was not a choice, it was a requirement. But multiverse theory faced a challenge. It explained why the universe appeared tuned, but it did not explain the origin of the foundational structure. It merely shifted the question one layer deeper. Why did some universes stabilize? And why did stability require such finely organized geometry? A final possibility lingered at the edge of scientific discourse. the simulation hypothesis. Not as a philosophical assertion, but as a theoretical framework for understanding informational structure. If reality behaved like a coded system with coherence, fine-tuning, and repeating patterns arising from informational rules, then the universe might operate like a simulation, not necessarily created by intelligence, but governed by informational constraints. In this view, the hidden structure beneath reality was not physical. It was computational. The vacuum's texture, the lattice-like cosmic network, the synchronization across distances, and the perfect precision of dark energy would all be features of an underlying code. The Planck scale would represent a fundamental resolution limit, a pixel size for spacknup. This idea did not imply a digital universe in the human sense. It pointed to a deeper truth. Reality might be emergent from information. Physics could be the manifestation of algorithms. The laws of nature could be expressions of data. The fine-tuning of constants could reflect stability conditions in an informational substrate. But the simulation hypothesis had its own weaknesses. It offered no clear falsifiability, and it raised philosophical questions no scientific model could comfortably address. Still, the resemblance of vacuum behavior to error-correcting codes, as noted in several theoretical studies, gave the idea a strange scientific foothold. As these theories unfolded, one pattern became undeniable. Every attempt to explain the hidden structure beneath reality pointed toward a deeper unity. Whether through quantum fields, loops of geometry, vibrating strings, holographic encoding, or multiverse survival, each theory suggested that space-time was not fundamental. It was derivative, emergent, a shadow cast by something deeper. And each theory, despite its strengths, also carried profound limitations. None could explain every observation. None could map the entire foundation. Each described only facets of the hidden architecture, like different languages trying to name the same indescribable truth. The strengths of these theories lay in their elegance, their predictive potential, and their alignment with observed anomalies. Their weaknesses lay in their incompleteness, requiring assumptions, approximations, or untested predictions. Yet the convergence was unmistakable. The universe looked structured because it was structured, whether that structure came from quantum fields or spin networks, strings or holographic boundaries, multiverse selection or informational substrates. The message was the same. Reality was not a chaotic accident. It was built upon foundations deeper than matter or energy, deeper than space or time. Theoretical physicists found themselves confronting a realization they had long avoided. The universe's hidden architecture was real, and every theory was merely a different reflection of it. The true nature of this structure remained elusive, but the fact of its existence grew harder to deny with each passing year. And beneath all these theories lay a question that no model could fully answer. If reality is built upon a deeper foundation, then what lies beneath that foundation? As the hidden structure beneath reality revealed itself in fragments through scattered signatures and cosmic radiation, faint alignments in quantum noise, and quiet harmonies in space-time geometry, the scientific world turned its attention toward a different frontier, the tools capable of uncovering the truth. For the first time in human history, technology approached a threshold. Instruments no longer reached only outward into the cosmos, they reached downward, into the fabric of existence itself. What once lay beyond the reach of observation now flickered at the edge of detection, like a distant light glimpsed through a veil. Around the world, laboratories, telescopes, detectors, and quantum systems converged on the same mystery. Not by coordination, but by necessity. Each device probed a different aspect of reality: light, gravity, energy. Information in each returned data that hinted at the same buried architecture. The search for the universe's foundation had become not just a scientific pursuit, but a global collaboration across disciplines. Each tool illuminating one part of an invisible whole. The James Webb Space Telescope became one of the earliest pillars of this new era of inquiry. suspended in the cold darkness beyond the moon's orbit. Webb's golden mirrors reached back in time to observe the first galaxies. Those fragile structures that formed when the universe was still young, with infrared eyes capable of seeing. Through dust and across cosmic epochs, Webb captured images of primitive star nurseries, warped galaxies, and vast gravitational arcs sculpted by dark matter. But beneath the aesthetic wonder, Webb's instruments gathered something subtler: the geometry of the cosmos. By mapping early galaxies with unprecedented clarity, Webb traced the influence of dark energy and the distribution of matter across billions of light-years. And in this cosmic architecture, mathematicians saw hints of deeper rules: spacing of galaxies, the curvature of ancient light, and the large-scale arrangement of cosmic filaments all bore the imprint of concealed structure. The universe expanded not as chaos would dictate, but as though responding to an underlying symmetry. Webb's data became part of a growing tapestry, a cosmic map of the hidden foundation at CERN. Far from the cold silence of space, another frontier emerged. Within the colossal ring of the Large Hadron Collider, particles collided at energies so immense they momentarily stripped reality to its bare essentials. In these collisions, the vacuum itself was exposed. The Higgs field responded. Fluctuations surged. Particles appeared from empty space, only to vanish again. What should have been a chaotic sea of randomness revealed subtle alignments and patterns hints, a vacuum behavior that did not fit standard predictions. Physicists searched in particular for signs of vacuum decay, a phenomenon predicted by quantum field theory in which the universe transitions to a lower energy state. Such a decay, if triggered, could collapse the foundation of space-time. But its absence was just as unsettling. The vacuum appeared more stable than theory allowed, fine-tuned, reinforced, as if some deeper structure held it in place. CERN's detectors captured anomalies and field interactions that suggested hidden thresholds, energy values at which reality behaved differently, like musical notes that only resonate at specific frequencies. These thresholds hinted that the vacuum was not a passive stage, but an active participant with internal structure. Some physicists began to suspect that the universe was balanced on quantum mechanisms far older than the Big Bang mechanisms that preserved stability through rules not yet understood. In distant laboratories, another kind of instrument took shape, one that probed the universe from the smallest scales rather than the largest. Superconducting quantum computers, operating near absolute zero, simulated quantum fields with extraordinary precision. Qubits arranged in carefully isolated systems recreated the behavior of fundamental particles and vacuum interactions. These quantum simulations revealed patterns that mirrored hints seen in the real universe: emergent coherence from randomness, self-organizing domains, and phenomena resembling miniature versions of space-time itself. Some simulations produce structures analogous to micro-wormholes, bridges between points in the simulated vacuum, arising spontaneously from entanglement and field dynamics. Others generated lattice-like arrangements that echoed the cosmic web on unimaginably small scales. These were not literal wormholes or literal lattice, they were mathematical analogs. But their repeated emergence, regardless of the system's initial conditions, suggested that the underlying mathematics of reality favored structure over chaos. These quantum machines became laboratories of existence, allowing scientists to explore hypothetical forms of space-time. They tested how geometry might emerge from entanglement, how constants might shift, and how vacuum states might evolve under different rules. Each simulation brought scientists closer to answering the question that had haunted cosmology. Was the hidden structure beneath reality natural, or was it emergent, born from deeper principles not yet encoded into physical theory? At the cosmic scale, dark energy surveys sought answers of their own. By measuring the expansion of the universe across many epochs, these surveys traced how dark energy behaved across space and time. The results were haunting. Dark energy acted with uniformity so precise it bordered on deliberate orchestration. Its density remained nearly constant across billions of years, refusing to fluctuate as normal fields would. Even in regions dense with galaxies, where gravitational influence was strong, dark energy maintained the same pressure, the same acceleration, the same invisible influence. For some scientists, dark energy represented the most direct evidence of the universe's hidden architecture. It behaved like a field that responded not to local conditions, but to global rules that governed the universe as a unified whole. It was as if dark energy operated through a deep algorithm, maintaining cosmic expansion with perfect fidelity. Future missions like LISA, the Laser Interferometer Space Antenna, promised to push this investigation even further, suspended in a triangular formation millions of kilometers across. LISA will listen for extremely low-frequency gravitational waves, waves so gentle they cannot be detected on Earth. These waves may carry the imprint of phenomena never before observed, the oscillations of space-time itself, the echoes of cosmic strings, or the faint tremors of exotic particles transitioning through vacuum states. If LISA detects patterns not predicted by general relativity, expected harmonics, or coherence, these anomalies could expose the structure beneath space-time. The waves may reveal whether space-time is continuous or quantized, smooth or granular. They may expose the architecture that has remained hidden for billions of years. On Earth, another type of instrument quietly approaches the same mystery: atom interferometers. These devices use ultra-cold atoms suspended in vacuum chambers to measure minute changes in gravitational fields, acceleration, and space-time curvature. They can detect variations on scales far smaller than any optical telescope could ever perceive. As atoms drift through perfect stillness, their interference patterns reveal tiny distortions in reality, the fingerprints of vacuum texture. Recent experiments hinted that the vacuum may not be uniform. Tiny fluctuations in the movement of atoms suggested microscopic variations that could reflect deeper structure. The patterns were subtle, nearly imperceptible, but consistent enough to spark debate. Were these fluctuations random, or did they hint at the grain of space-time, the fine threads woven together at the Planck scale? Across all these tools, one theme emerged. Humanity had begun to measure the boundary between known physics and the unknown architecture beneath existence. And each experiment asked the same profound questions. Was the hidden structure natural, an inevitable consequence of deeper laws that had existed since the universe's first moment? Or was it emergent, arising from the interactions of fields and geometry in a way no theory had yet explained? But the constants of nature change. Were they fixed by unseen mechanisms, or were they merely historical outcomes of a cosmic selection process? And the deepest question, was space-time continuous? Or was it quantized, built from indivisible units that formed the foundation upon which all else was constructed? Some scientists believe the constants could shift under extreme conditions. Perhaps in the earliest instance of the Big Bang, the laws of physics evolved, settling into stable forms only when the universe cooled. If so, then the hidden structure might be the residue of this ancient evolution, the fossilized framework of the universe's infancy. Others propose that the constants were protected by symmetry's mathematical relationships that enforce stability. In this view, the hidden structure was not a relic, but a rule. A deeper grammar of reality, a more radical possibility suggested that deeper layers existed beyond the Planck scale layers that science had not yet imagined. These layers might determine the behavior of all physical law, shaping the vacuum, stabilizing space-time, and maintaining coherence across the cosmos. If these layers could be detected through anomalies in gravitational waves, through shifts in quantum simulations, or through signatures in ancient light, then humanity would be confronting the deepest truth ever uncovered. Across observatories and laboratories, scientists held quiet debates. Could the structure beneath reality ever be fully revealed? Or was it woven too deeply into the fabric of existence to be unraveled? The tools humanity had built, Webb, CERN, quantum computers, dark energy surveys, LISA, TAMA, interferometers, were powerful, but the mystery remained older than time itself. Yet still, they tried. Not because they expected immediate answers, but because the search itself was an affirmation of human curiosity. It was a testament to the idea that understanding the universe was worth the struggle, even when the answers lay beyond the horizon of certainty. In the cold silence of space, Webb waited for ancient photons that had traveled billions of years to reach its mirrors. In underground tunnels, particles collided, tearing reality open for an instant before closing again. In quantum machines, chilled to near absolute zero, tiny systems recreated the behaviors of entire universes. In vacuum chambers, drifting atoms felt the faint pull of geometry hidden beneath emptiness. And in supercomputers across the world, simulations attempted to predict what lay beyond space-time. Each tool reached for the same truth: was the hidden structure beneath reality a fundamental layer of existence? Or was it a shadow of something deeper, something yet unseen? These were not merely scientific questions. They were philosophical, existential. They touched the boundaries of knowledge and the meaning of reality itself. And as the instruments continued their relentless search, the universe remained silent. Silent, but not empty. Silent, but structured. Silent, but waiting, in the long journey of discovery. Humanity has peeled back countless layers of the universe, revealing forces, particles, and structures once thought inaccessible, yet now at the threshold of the deepest mystery ever encountered. A strange silence settles over the scientific world, a silence not of ignorance but of awe. For beneath every experiment, beneath every dataset, beneath every equation lies a truth more profound than any single discipline can contain. Reality has structure, not the familiar structure of stars or atoms, nor the gravitational scaffolding that binds galaxies into sprawling webs. This structure lies beneath all of that, beneath space-time, beneath the vacuum, beneath the quantum fields pulsing invisibly across existence. It is the architecture of being itself, older than time, deeper than light, more mysterious than the forces that shape the cosmos. And now, as humanity begins to sense its outline, a profound question rises like a tide. What does it mean for reality to have structure at all? For generations, science assumed that beneath complexity lay simplicity, that beneath stars lay atoms. Beneath atoms lay particles, beneath particles lay fields, and beneath fields lay randomness. But now the opposite appears true. Beneath the apparent chaos lies order and orchestration so precise that it cannot be dismissed as coincidence. The laws of physics behave as though anchored by hidden principles. Space-time behaves as though woven. The vacuum behaves as though encoded. And the universe, far from being an accident born of chaos, behaves like something constructed upon a foundation. This realization forces a quiet reckoning with humanity's place in the cosmos. For if the universe is structured, then the human mind, the observer, the questioner, thinkers witnessing not just matter and motion, but the deep groundwork of existence. This is a responsibility weighted with humility. Humanity, a species that evolved on a small, fragile planet around an ordinary star, has reached out into the void and touched the edges of creation itself. It has measured the trembling of space-time, traced the harmonics of ancient light, watched the dance of particles emerging from emptiness. Yet even as these discoveries expand humanity's reach, they shrink its sense of scale. The universe remains vast beyond comprehension, its structure stretching across billions of light years, its origins hidden behind a veil no telescope can yet pierce. Human life, brief and delicate, flickers like a momentary spark in comparison. And still, that spark illuminates the darkness. It asks questions no other creature has ever asked. It seeks understanding not for survival, but for meaning. This paradox, though, smallness of humanity and the depth of its curiosities, perhaps the most remarkable feature of the cosmos. For in observing the universe, consciousness becomes aware of its own origins. The observer and the observed trace their lineage back to the same hidden structure. The atoms in the human brain, the photons that strike the retina, the vacuum in which those photons travel all arise from the same foundational architecture. The universe contemplates itself through the minds of those who study it. The structure beneath reality becomes aware of its own existence, reflected through consciousness. This raises a profound philosophical dilemma. If the universe has structure, it is built upon hidden geometry, encoded information, or fundamental symmetries. Then why does that structure exist at all? Why is there a foundation instead of nothing? Why do the laws of physics obey rules? Why do constants hold their values? Why does reality arise from anything other than emptiness? Stephen Hawking captured this dilemma in a single haunting question. What breathes fire into the equations and makes a universe for them to describe? For equations alone do not create reality. They are descriptions, not causes. They sketch the patterns, but they do not explain the canvas. Some deeper principle, some primordial truth gives rise to the architecture beneath existence. And this truth remains hidden, even as the structure it supports becomes increasingly visible. This philosophical tension is not new. Ancient thinkers wondered why the heavens moved with such rhythm, why nature followed rules, why mathematics described the world so elegantly. But only now, after centuries of observation and theory, does a possibility emerge that reshapes those old questions. The universe may follow rules because the rules emerge from a deeper foundation, one not composed of matter or energy, but of structure itself. If the universe is structured, then its existence is not arbitrary. It follows from something, though what that something is remains unknown. Perhaps the foundation is natural, a consequence of timeless laws beyond perception. Perhaps it is emergent, a product of interactions more intricate than any framework humanity has yet imagined. Perhaps it is selected a survivor in a multiverse of unstable realities. Or perhaps it is informational and expression of patterns that exist outside of space and time. But whatever the answer, the structure beneath reality forces a confrontation with a truth both humbling and empowering. The universe is comprehensible. Not fully, not yet, but enough that human minds can grasp fragments of its architecture. Enough that patterns reveal themselves in the cosmic microwave background. Enough that harmonics echo in gravitational waves. Enough that the vacuum whispers through quantum fluctuations. And yet, the deeper humanity looks, the stranger the universe becomes. For every insight, a deeper mystery emerges. Every explanation reveals a new level of structure. Every discovery reframes what came before. Cosmos behaves like an infinite library, where each shelf contains books describing the shelf below, and every book opens to reveal another beneath it. The deeper one descends, the more profound the questions become. The more clearly the architecture is perceived, the more impossible it seems that such structure could arise from randomness. This is not a journey toward certainty, it is a journey toward understanding that certainty may never be reached. The universe offers clues, but withholds conclusions. It reveals patterns, but obscures origins. It allows humanity to glimpse its structure, but not its purpose. And yet, perhaps purpose is the wrong question. Perhaps the universe does not ask to be interpreted through intention or design. Perhaps meaning arises not from the cosmos itself, but from the consciousness that contemplates it. The structure beneath reality does not demand explanation. It simply is. But humanity, in observing it, creates meaning born from curiosity, wonder, and the desire to know. This, then, is the emotional heart of the mystery. The hidden structure beneath reality is not merely a scientific puzzle. It is a mirror reflecting the nature of existence and the nature of those who seek to understand it. It reveals that the universe is not empty. It is not chaotic. It is not indifferent. It is structured, coherent, harmonious. And through that structure, life arose. Life capable of perceiving the foundation of the cosmos and asking the deepest questions imaginable. The final truth of this journey is not that humanity stands on the edge of discovery, but that it stands on the edge of understanding itself. For the more clearly the universe is seen, the more clearly the human condition is revealed. Fragile, brief, and finite, yet capable of grasping the infinite, as the scientific tools continue to probe the vacuum, map ancient light, and listen to trembling space-time. The structure beneath reality comes into sharper focus. And with each revelation, the horizon of knowledge expands, not outward, but inward, toward the very essence of existence. Perhaps the hidden structure beneath reality will one day be fully understood. Perhaps its origin will be revealed. Or perhaps it will always remain just beyond Risa, truth too deep, too vast, too fundamental for any mind to fully comprehend. But even if the mystery remains, its pursuit is enough. For in seeking to understand reality, humanity discovers meaning not in the answer, but in the journey itself. And so the story ends where it began, with a universe that is silent, ancient, and impossibly structured. A universe that invites exploration, but never reveals all. A universe that holds within its depths the architecture of existence. Waiting for those curious enough to ask the unanswerable, humanity stands at the edge of understanding, the very source of reality. And the deeper it looks, the stranger the universe becomes. If questions like these spark your curiosity, then make sure to subscribe to Late Science Universe and hit the bell icon so you never miss our next journey into the greatest mysteries of the cosmos. See you in the next video. Thank you. Poetic lines. Beyond the stars lie worlds unseen, and Late Science Universe still has many dreams to explore.